Hey, hello and welcome back to CB Astronomy. Again, my name is Chris and I'll be your host for the next, I was going to say X minutes because I'm not entirely sure how long this video is going to go on for, but should we crack on? Today's video is the afterlife of a star. So just the remnants of the massive stars and small stars and the variations that occur. I covered a bit of it in my stellar evolution video, but I felt that given the variety of what can happen after a star dies, I felt that it warranted its own video. So for small sun-like stars, again I briefly covered it in my stellar evolution video, but if you haven't watched that, just a quick summary. So once the core of the star, like our sun, is after fusing all its hydrogen into helium and then helium onto carbon, the outer layers of the star will expand and cool and shine less brightly, leaving behind a white dwarf which will eventually cool and dim and stop and shine less brightly itself. So when it stops shining, it's known as a black dwarf. But when a white dwarf is also responsible for a type of supernova called a type 1a supernova. Now the reason that these supernovas are particularly interesting is because they shine with the same luminosity every time. So they're really good for using as landmarks, and because they shine the same brightness every time, you can use them to get the distances of other distant galaxies or stars. So they're really interesting that way. But one of the other points I just want to make is that one of the most brilliant things about the universe is its cyclic nature. So it's like a big recycling machine. It will take the materials made from a star, disperse them into space, and like those materials will go on to make new stars and make new planets and people and stars and cabbages and everything. So everything, like every atom in your body was once in the heart of a star that got dispersed out due to a supernova explosion. And I think that's just absolutely brilliant. It's amazing how the universe recycles its matter. But another point is that I think that humans are an amazing species because we are the only species that we know of that has been able to like figure all this out and make mathematical models of the universe. And so I think it's brilliant that humans as a species are able to figure all this out. It gives me a bit of hope for humanity in the future. But so we'll move on to massive stars. So again, in the stellar evolution video, I mentioned a thing called neutron stars. Now I'm going to mention three types of neutron stars today. So that's magnetars, X-ray binaries, and pulsars. Now I'll tackle the magnetars first. Now, as their name suggests, they emit a strong magnetic field. So before I start talking about the magnetic field, I want to go into like the anatomy of a magnetar. So the magnetar is the remnants of a core of a massive star that went supernova, and the core was between 1.5 to 3 solar masses. So this is just a really dense object that's going through space, but it has the mass of about 2 to 3 solar masses. So that's 2 or 3 suns compressed into the space of about 20 kilometers. And like I just can't fathom like how heavy this material is. When I was doing my research into the video, they were saying like a single teaspoon of this material would weigh 20 to 30 million tons. So it just amazes me that like the matter can actually get that dense. But sorry, back on topic. The magnetars also rotate very quickly, so I think they can rotate up to once every second, or maybe a bit quicker. But the sources that I looked up said it was just one rotation per second was their max. So back to the magnetic field. So due to the high temperature, the rotation, and fluctuations in the magnetic field, this produces a lot of X-rays and gamma ray bursts. Now, the gamma ray bursts in particular can be really, really harmful to any nearby planets, because they're just so high energy that they just strip the atmosphere off a planet in seconds, leaving a potentially thriving planet with life, barren rock just floating through space. But thankfully, there's none in the local vicinity to Earth, and we can safely detect them because they lose most of their energy by the time they arrive at Earth. The first one I think was detected in 1979, but the magnetar theory was only put forward in 1992 and quickly became widely accepted as the reason for these gamma ray bursts that were being detected. What else do I have? It's estimated that there's about 30 million magnetars in this galaxy alone. Now, they only live for about 10,000 years, so a lot of them that we may have detected from further out would more than likely be long gone. We're just seeing the remnants, but I'll go into how light works and how radiation works in space in a video in a couple of weeks. But so the second neutron star I'm going to talk about is an X-ray binary. Now, these form from a binary star system, so they'll have two stars orbiting each other in close proximity, as well as planets and moons and other bits and pieces in the solar system. So I know a lot of my Star Wars brethren will be picturing Tatooine and the binary star sunset. So that's more or less what I like if you were standing on the surface of one of the planets that are orbiting the two suns. But that's not the point of interest at the minute. So the way these binary star systems work is the larger of the two stars will evolve quicker than its companion star. So that will eventually go through its life cycle and go supernova, leaving behind a neutron star or a black hole. Now, we'll stick to the neutron star example for now. But so you'll have one star maybe mid-lifespan and then one neutron star orbiting it. Now, because of the density of the neutron star, it will suck a lot of the outer layers off the companion star and form an accretion disk. Now, what happens then is the material will heat up as it's orbiting the neutron star, and the neutron star will then start emitting quasars because it's taking in too much material and it can't handle it, so it emits it back out at its poles in these really high energy beams, and that's where the X-rays come from. But so the smaller companion in time will also go supernova. And again, if you'd like more detail on supernovas and what happens and what makes them, go back and watch the stellar evolution video. But so the smaller star will eventually go supernova and leave we're going to say it's going to leave a neutron star as well, just for the sake of this argument. So so you'll have two neutron stars then orbiting each other, and this is really brilliant because they're so dense and they're emitting such radiation, they're orbiting each other so fast, and they will eventually collide with each other, but they will produce a thing called gravitational waves. Now, Einstein predicted these in his theory of general relativity, in that space itself can be stretched and compressed like ripples on a pond, and it amazed me at the intelligence of that man to predict that over 100 years ago, and for scientists now to see this. Now, it takes really specific detectors to prove these, and that's why it's been so difficult to prove till now. But now that we have them up and running, we've detected them a few times in the last year or so, and I think it's brilliant. And congratulations to Mr. Einstein for being so clever as to predict that. But yeah, so there's two types of X-ray binary, high mass and low mass, and the one that I was just discussing is the high mass one, where it takes the mass off its companion star. The low mass binary X-ray, the low mass X-ray binaries are a little bit different. There isn't a definite theory on how they form, but the leading theory is that you'll have a dense object roaming space that will have a gravitational interaction with a star or a cluster of stars, and it'll steal a companion that way. Same thing happens, but it's a lot more controlled because they'd be further out from each other than high mass now. So the X-ray bursts are, or the X-ray emission is in bursts and transits. So just trying to picture that, like, we can only see it when it happens to hit Earth and be picked up by our detectors, but there's a lot of, because of the transient nature, you can only see it when it's like it itself has like an on and an off position if you're observing from Earth. So it makes it really difficult to predict exactly how many of the low mass binaries there are. But yeah, unfortunately that's all the information I have on them. Sorry. Yeah, great. I am after tripping myself up, and that's quite embarrassing. But yeah, the final type of neutron star that we'll talk about is the pulsar. Now, pulsars are particularly interesting to me because they emit a beam of electromagnetic radiation, and this can only be observed when the beam is facing Earth. But the metaphor that is often used to describe these pulsars is a lighthouse. In fairness, it is a good one. So if you can picture yourself on a ship just off the coast of whatever country you're from, so you will see a periodic light flashing at you. So you just see flash, 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 and then, like, it, obviously we all know what a lighthouse is for, but these intergalactic lighthouses make it really good for navigating the universe in the future, and I can't wait to see how scientists go on to use them. Yeah, in rotation power pulsars, the beam is caused by the rotational energy of the neutron star, which generates an electric field from the movement of the strong magnetic field that's produced by it initially. Just as a quick side note, the link between electric and magnetic fields is really, really interesting, but it's not in my immediate plan for the future. However, if you'd like to see a video on it, hit me up and I will look into it and write a script and record a video. Anyway, back on topic. Yeah, so the electric field produced results in the acceleration of protons and electrons on the surface of the star, and so this charge will go to the magnetic poles, and then that's where the beam of EM radiation gets thrown out from the northern and southern poles. Yeah, the pulsars have a really long lifespan. They can go from, between 10 and 100 million years was the number that I found when researching this video. But yeah, as I can't wait to see how scientists begin to use them in the future. Hopefully it's in my lifetime that we start branching out to other systems. I really hope it is. Actually, just another side note here. The closest star to Earth is Proxima Centauri, and that is a red dwarf. So that's a star that's smaller than Earth, and it burns for potentially trillions of years. But because it's 4 light years away from Earth, I think. But yeah, scientists observed planets orbiting this, so that was going to be one of the potential candidates for the first voyage into space. But unfortunately, after finding out there only the other day, I read that it was hit with a really big solar flare, and like it just really bums me out that like apparently the planet like shot up with as much as 10,000 times its luminosity because of the intensity of this solar flare that hit it. But yeah, it's a bit of a shame. Sorry, back on topic. Yeah, finally I'm just gonna briefly talk about black holes and what happens. Yeah, so black holes happen when a really, really big star, like there's a monster of a star, explodes and the core is larger than 3 solar masses. It will contract on itself and form a black hole. Now, black holes are particularly fascinating to me because I find it really difficult to visualize the entity itself. I've seen illustrations of the accretion disks around the black holes, but to picture the black hole itself, like when I think of a hole, I just think like a hole in the ground, a couple of meters in diameter, a couple of meters in depth, and that's fine, that's a hole. But to try to visualize a 3-dimensional hole, like a complete sphere that matter will fall into, like I just find it really, really difficult to visualize, and that's what makes it so interesting to me, and I really want to understand them more. And I do have a video on the pipeline for the implication of black holes from the beginning of the universe to current day and beyond. So I can't actually talk about black holes too much in this video, unfortunately. But just a little bit of information about them. They can range from a couple of microns across to astronomical units across. Now, an astronomical unit is the average distance between the Earth and the Sun, which is about 150 million kilometers. But yeah, so there's supermassive black holes like at the hearts of galaxies. So like because they have such a wide range of microns to 400 astronomical units, I just find it so fascinating. Like this entity can be any size, it doesn't discriminate. The matter it finds, it takes in whether like it takes in light, radiation, other black holes. But yeah, I'm getting ahead of myself, and to avoid spoilers on a future video, I'm going to leave it here for today. Really sorry that I can't go into more detail on the black holes, but in about a week or so or less, you'll have a video on black holes and all the information about them that you can handle. Yeah, I really hope you enjoyed the video. I apologize for stammering so much in this video. I just find this really an exciting topic, and I kind of get a bit ahead of myself. No matter how many, like even when I rehearse the script, I still deviate and get distracted and excited. But yeah, thanks very much for watching. Like and subscribe to the channel. Follow my Instagram and Twitter. The links will be in the description or maybe in a corner of the video. But yeah, thanks very much for watching. Hit me up with any topics you want me to cover. See you later.